Welcome to the Computational Fabrication Seminar. We have two speakers for today's session on computational art. Professor Xiaoming Fu will first give a motivational talk, and then Kang Wu will give a deep dive talk. We have a short Q&A session at the end of the two talks. Xiaoming Fu received his bachelor degree in 2011 and a PhD in 2016 from University of Science and Technology of China. He is currently an associate professor at the School of Mathematical Sciences, University of Science and Technology of China. His research interests include geometric processing and computer-aided geometric design. Professor Xiaoming Fu's talk will be on geometric-driven art design. The floor is yours, Xiaoming.
Thanks for the introduction. I'm Xiaoming Fu from the University of Science and Technology of China. Glad to be here to discuss the geometry-driven art design. Geometry is a branch of mathematics that studies the size, shape, position, and of 2D shapes and 3D figures. Geometry is used daily by almost everyone. In geometry, you are exploring spatial science and geometry reasoning. You can find geometry in art, architecture, engineering, and much more. To process this kind of geometry data using computers, the geometric computing was the generator. There are many topics such as parameterizations, deformations, remeshing, and segmentation. In this talk, I will discuss our efforts to apply these techniques to art design. The first work is about mesh cutting and parameterizations used for art design. The artist Okada pierced citrus fruits into a variety of elegant 2D shapes, such as animals, plants, and cartoon characters. This art form is called citrus peeling art. Based on the conservation concept, each shape must be created using one entire pierce. His artworks have become popular and are widely used in children's education. It is said that 1 out of 5 Japanese knows about this art. To create new samples of this art form, Okada needs a large number of trial and error experiments. This construction process is tedious and time-consuming. Our goal is to propose a computational algorithm for this art form so that it allows general people to design new shapes. Given an input shape, this problem seeks to find a way to generate a cut path on a citrus fruit in order to unfold it into a 2D shape that is close to the input with low isometric distortion. However, this problem is very challenging for 2 reasons. First, it is non-trivial to optimize the similarity between the input shape and the unfolded shape. Second, the input shapes are not always possible to express using citrus peels. Users should be able to modify an input shape to find a suitable solution. It is very difficult to construct cut passes so that the unfolded shape of the cut citrus is similar to the input. However, it is easier to map the input shape onto the citrus to try to completely cover it. So the key insight of our method is to convert the cut generation problem to a mesh mapping problem that is easier to solve. Some input shape can be isometrically mapped to completely cover the citrus. Then the boundary of the mapped shape can be used to generate the resulting cut path. Some input shapes are unable to completely cover a citrus. This is an example. The input shape cannot cover all citrus after the mapping process. For these input shapes, we involve users in the design process by proposing an iterative design process. The mapping process and the interaction process are alternating performed to meet user design intentions. After the iterative design process, the mapped shape almost covers the features and can be used to generate the resulting cut paths. We show example for real peeling. During the real peeling process, a user first draws gratitude on a real features. Then the user draws the cut path on the citrus fruit according to our gratitude-based guidance. Finally, the user crafts the citrus fruit along the draw cut and unfold it. This is the example by ourselves, generated by ourselves. They are animals, plants, and cartoon characters. The second work is still about the mesh cutting and parameterization. Developable surfaces have been widely used in various designs, such as papercraft, ship hull, clothing, and architecture. Our goal is to approximate a triangular mesh with piecewise developable patches. We need to introduce the cut to make for the segmentation. Each patch should be discrete developable and can be flattened without any overlaps. Then the number of patches should be small, and the similarity between the input and output meshes should be high. To solve this problem, our key observation is that a deformed mesh after enforcing discrete developability is easily partitioned into nearly developable patches. Based on this key observation, we first deform the input to a nearly developable meshes by optimization of developability encouraged deformation energy. Then we use a cost-to-fine strategy that first produce a over-segmentation based on the normal difference between adjacent triangles, and then reduce the number of patches based on the discrete Gaussian curvature. Finally, we refine the segment mesh to improve the discrete developability while ensuring that the approximation area is small, each patch is smooth, and the seams between the patches are smooth. Here are several approximation results. In practice, our algorithm achieves a favorable trade-off between the number of patches and the approximation area. The fabrication process including two steps. First, we print the flattened shapes into the paper sheets and cut it. Second, we bend the cut patches and stick them up. This is the fabrication result of the bunny model. Here are the more fabrication results by ourselves. This paper has been accepted by the SIGGRAPH 2022, and you can find and the fabrication process is selected in the technical paper trailer. You can find the fabrication process. And the next work is using the remeshing techniques for the art design. The first work is about the modular modeling. The reusability of panels is an important issue in art and architecture. For example, building the art tech scheme made of several types of the same shape will greatly reduce the cost of the processing, transportation, installation, and maintenance. In the ancient Chinese jigsaw puzzle game. One can use several pieces of the same type to form different patterns, but the results are only be 2D. Our goal is to provide a computational algorithm to model and fabricate different shapes with the specified discrete equivalence classes of triangles. Since we have to use the same type of templates to match different models, the topology and the geometry of the mesh needs to be changed. This is a remeshing problem. The modeling process is formulated as a constraint optimization problem. The variables are the mesh topology and the geometry. The objective function is the fabrication error defined as the maximal matching error of all triangles. The constraints are to keep the shape similarity and the mesh smoothness. Since the fabrication error is the worst case on a certain triangle, we propose a practical algorithm to iteratively perform local operations, including edge collapse, edge flip, and vertex relocation to solve the constraint problem. These operations are carefully filtered to satisfy the smoothness and approximation constraints. This is a demo to show the greedy remeshing process. For real fabrication, we first select the templates based on the instruction, then bend the stainless steel hinges to match the target angle, and fix the triangle plant and hinge using nylon cable tiles. The assemble process for two nearby triangles is straightforward, and this process is used to manufacture the entire model. This is the fabrication results of the Barney model. Here are more fabrication results by ourselves. All of the models are made based on the same 9 triangle templates. The last work is still using the remeshing for chipshift nets. Discrete chipshift nets are quad meshes with all edges of the same length. They are widely used in architecture, engineering, and art design. Our goal is to provide a computational tool to allow general users to fabricate discrete chipshift nets of their desired model at home. From a geometrical perspective, this process is a quad remeshing problem. We use the parameterization-based methods for generating discrete chipshift nets. It first computes a frame field, then constructs a global seamless parameterization, and finally extracts a quad mesh. The frame fields are essential. According to the requirements of the discrete chipshift nets, the frame fields are required to be discrete integratable, unity length, and angle bounded. To generate such fields, we use 2 field representations. The vector pair representation is used in field-to-Jacobian process to enforce the integrability. The complex representation is used in the Jacobian to field process to approach unity length while bounding angles. These 2 processes are alternatingly conducted. This is a demo to show the alternating optimization process. With our frame fields, we first extract the quad meshes using previous parameterization-based method, and then optimize the mesh to achieve nearly identical edge lengths. Here are several digital nets. We provide a detailed specification for general users to use common tools to fabricate discrete chipshift nets at home. According to the length information, we first craft each patch from the wheeled wire mesh. The tangential and normal deformations are used to deform each patch to match the target shape. During the merging process, the patches are assembled one by one. We iteratively deform the patches so that the corresponding patches can be assembled smoothly. This is the result of the Raptor model. This is more. Here are the more results. The next work is using mesh deformation for minor cup and sorter art. Kang Wu will introduce the algorithm in details. So the geometrical computing techniques are useful for art design. However, there are some feature works. First, I think use the FEM simulation to allow the designed artworks to be physically made is very important. I think we can explore more work in this direction. Second, we can consider more physical phenomena. For example, optics is closely related to the visual art. So we can use the rendering techniques in computer graphics to assist us in the art design. Thank you.
Okay, thank you, Xiaoming, for the inspiring talk. Our deep dive talk will be given by Kang Wu. Kang Wu is currently a PhD student in the School of Mathematical Science at University of Science and Technology of China, under the supervision of Professor Li Gangliu, Professor Ren Jiechen, and Professor Xiaoming Fu. His research interests include computational art and 3D modeling. Kang Wu's research talk will be on computational mirror cup and source art. So Kang Wu, now the floor is yours.
Okay. Hello, this is Kang Wu from the University of Science and Technology of China. I'm glad to be here to give a talk. My talk consists of two parts. In the first part, I will briefly review the studies on 3D visual art design problem and show my idea about how to solve it. In the second part, I will formally introduce our work, computational mirror cup and source art, and use it as an example to prove my idea. 3D visual arts refer to the 3D artworks experienced primarily through the sense of sight. Artists use their rich imagination and experience to design 3D objects to give the audience a memorable experience. However, the design process takes a lot of trial and error. So this has attracted the attention of many researchers focusing on proposing various algorithms to simplify the initial complicated design process and help artists quickly realize the art in their minds. Where there are many studies on 3D visual art design problems. According to the types of art, I simply divide them into 4 categories: shadow, reflection, and others. And within each category, I subdivided these studies into subcategories according to the problems they solve. Next, I will simply introduce the problems studied in each category. The first one is shadow. We have 2 subcategories in this kind of art. The first subcategory is shadow art. The researchers studied how to modify the object's shape or even color so that when placing under specific light source, the casting shadows form their desired patterns. Here we show 2 examples in the subcategory. The 2 works investigate how to generate ambiguous shadow art sculptures. Researchers need to optimize the shape of the object itself based on the difference between the shadow pattern and the target pattern. We can see that when illuminated by light in a specific direction, the sculptures automatically generate by algorithms are able to project the user's desired pattern on the receiver. The second subcategory is self-shading images. Unlike the previous kind of shadow art, these artworks use the shelf occlusion to form shadow images. That is to say, the shadow receiver becomes the object itself. As we show, the shadow pixel proposed by Romano and others built walls to cast the shadows on a plane to create a self-shading image. And Alexa and Matusik choose to make pits on a plane to create self-shading images. They found that increasing the depth of the hole causes it to appear darker. So their result is grayscale image, not binary image. At present, the work in this direction is limited to create self-occlusion shadow art on plane. I think in the future, maybe we can make it on more complex and interesting surfaces. The second category is reflection. We divided it into 3 subcategories according to the variable to be optimized in their problems. The first subcategory is optimizing mirror. As the name suggests, researchers choose to optimize the shape of the mirror to get their designed visual effect. I picked 2 representative work in this subcategory. The first one is fabricating microgeometry for constant surface reflectance proposed by Weyrich and others. They manufactured a mirror height field to reflect light source to form a target image. The second one is the portal, designed and the fabrication of incidence-driven screen proposed by Osain and others in 2018. Their result consists of 2 parts. One is an input image served as a palette to offer RGB values, which is the Mona Lisa in the figure. The other is mirror grids used to reflect pixels in the left image to form the target image, which is the right image in the figure. Their goal is to calculate the configuration of mirror grids so that users can see target image in the mirror. The second subcategory is optimizing object. Different from the previous subcategory, in this subcategory, object shape and the color are optimized, while the mirror is fixed. Our work is in this subcategory. We deform the social mesh and calculate the color on it so that people can see 2 different images when placing the social in front of a mirror cup. The problem Sakurai and others studied was similar to that of ours. Their result can show different images when viewed from different directions. And their solution is to generate microstructures consist of colors and the walls on a reflector. So when viewed at a certain point, people can only see part of the reflector. This makes it possible for them to place different images on a reflector. The last subcategory is optimizing reflectance. In this type of visual artwork, the mirror is no longer one of the components. The reflectance of the object is optimized, and under specific light source, the object can show the targeted visual effect. This is somewhat similar to self-occlusion images, but not about shadows. Creating reflectance functions shows how to design the reflectance of an object so that patterns on its surface can be seen as a real 3D object under different light conditions. They selectively print ink on the surface to control the highlight part of the surface, while relief as image studied how to hide a second image in bas-relief. The hiding image can be displayed only under a certain light source. There are methods to optimize a height field represented by a triangular mesh to achieve the goal, since the normal of each face can affect its brightness under the light source. The third category is refraction, consists of three-part caustic, volumetric display, and other refraction art. The caustic is a kind of visual art that uses one or more designed lenses to refract the light to form a caustic pattern on a receiver. This is a typical inverse problem. The researchers need to adjust the shape of the lenses according to the error between the caustic image and the target image. Solving this problem is difficult because we cannot obtain the gradient from images to the landscape. But the optimal transport map or other methods such as differentiable rendering is used to handle this. Volumetric displays can directly render a 3D image in space, similar to the shadow art we mentioned before. The artist can display multiple images in the same volumetric display when it is viewed at different points. The volumetric display usually is made of transparent materials such as glass, so the influence of reflection is to be considered when they design the display. The figure shows a result generated by Hirayama and others. Their algorithm allows 4 different images to be placed in a cylindrical volume display. However, the image resolution and the clarity generated by their algorithm is not very high. I think this is a direction that can be improved. The last subcategory is other reflection art. Yue and others proposed a method for generating a puzzle kind of reflection visual art. From an entertainment point of view, they made the number of sticks the user had in advance equal to the number of pixels in the target pattern. Once a user inputs an image, their system will automatically compute a combination of sticks to refract the light for display this target pattern on the receiver. According to the result, the user could assemble the sticks to enjoy creating visual art. The work of Pubs and others presented an approach to generate device that can deform the original pattern to display hidden images. Their device consists of a lens array. In the figure from left to right are the original pattern, the lens array, and the hidden image. The last category is others. And I also divided into 3 subcategories according to the artworks they generated. The first subcategory is anamorphic objects. Anamorphic objects can only be viewed correctly at a certain viewing point. The studies on the design problem of this kind of artworks are usually use some existing rendering algorithms or industrial design software to simplify the design process of creating the anamorphic objects. For example, in anamorphic freeform deformation, they use desired surfaces or volumes as deformation tools to create anamorphies. And Hosseini and others introduced an algorithm to create anamorphic architecture. Their algorithm builds objects that satisfy constraints by reversing linear perspectival projection to convert the input 2D image into 3D space. The second subcategory is illusion objects. An optical illusion is something that plays tricks on our vision. This kind of 3D artwork utilizes human perception of 3D space and the experience of the structure of 3D objects to mislead the user, causing him to draw wrong or even contradictory conclusions about the shape of the object. ARPA and others presented a method for generating objects consist of 2D image and 3D components. Their results preserved part of the 3D theme, allowing the user to get a more realistic 3D experience when viewing them. Tong and others presented a novel approach of creating self-moving objects using hollow face illusion. When people view it from different viewpoints, they will find the objects had moved together with them. The key to this method is to take advantage of the fact that human prefers to interpret faces as convex rather than concave. The last subcategory is impossible objects. The artist mainly uses the depth misperception caused by projection to create topological structure that seems impossible to exist. Wu and others studied how to model and render such objects. They choose to use thin plant spline warping to deform the object so that in a certain viewpoint, the object seems impossible to exist. While Reyes and Charcoal used the standard CAGD techniques such as homogeneous coordinates and non-uniform rational B-splines to deform the object along racial lines through the viewport to create impossible objects. Although there are so many different types of 3D visual art, I think there is a commonality between these 3D visual art design problems. For a 3D visual art design problem, the goal is often a target pattern or a desired visual effect, and the variables are shape and the color of the object. That is to say, in a 3D visual art design problem, the researchers need to optimize the object to get a certain rendered result. And the optimization process is usually like this. The researchers use same parameters to render a result, and then they update the parameters according to the difference between rendered result and the target. This is a typical inverse problem. So we can use a general framework to describe these design problems. The target result or the desired visual effect can be represented as images. So the objective function consists of an image error term and some other constraint terms. And our goal is to optimize the same parameters, such as the light source, the object's shape and color, and so on, to decrease the image error between the rendered image and the target image. But that still remains a key problem. According to the optimization process we mentioned before, we need to update the same parameters to decrease the difference between target and the rendered result. But if we use standard rendering pipeline to render images, it is very difficult to do this because we cannot obtain the gradient from images to the same parameters. However, the differentiable rendering can help us overcome this problem. The differentiable rendering technology allows us to obtain the gradients of the rendered image. Using it to render images makes our objective function differentiable. Then the conventional numerical optimization algorithms can be applied to solve the inverse problem. Next, I will introduce our work and show how we use this general framework to solve a 3D visual art design problem. The mirror cup and the source art is a kind of attractive and interesting visual art. The artist skillfully designed the shape of the saucer, allowing people to appreciate the image on the saucer in both direct and reflected views. This art is appealing as the two views are in harmony, rendering it a more integrated art piece. The key idea of this kind of artwork is to make part of the saucer directly be visible to the viewer, while the other part of the saucer be occluded and can only be seen as a reflection through a mirror cup. However, it takes tremendous effort and it's a tedious and error-prone process for the artist to manually design and carefully tune the saucer surface in order to distinguish the perceived images in both the direct and the reflect views. In fact, the artist usually use a fixed wavy or corrugated saucer to create their artworks. This undoubtedly limited the shape of the saucer. But if we want to specify the two images and the shape of the saucer, if we want to specify the two images and the shape of the saucer, in this case, it is nearly impossible to find a solution, since not all saucer shape can adequately resolve the conflict between the reflected and directly viewed areas. Thus, tailoring a new shape for each set of input images is not an easy task, making it highly challenging to produce mirror cup and source art with desired images and the source shape, and the saucer surface. So to help artists to solve this design problem, our goal is to propose a general computational algorithm for the mirror cup and the source art design. Without loss of generalities, we assume that the input mirror cup is a cylindrical surface. Our algorithm takes two input images and a saucer as input, and it will automatically generate a textured saucer mesh as the output result. When placing the result mesh in front of the cylindrical mirror cup, the reflected and the direct views of the saucer match the two input images, and the saucer surface needs to be close to the input saucer shape. As we mentioned before, the 3D visual art design problem can be formulated as an inverse problem. So the objective function in our problem also consists of image error term, soft constraint term, and hard constraint term. In this case, the image error term is the visual difference between input images and the rendered images. The soft constraint is the deformation distortion term, and the hard constraint is the shape deviation constraint. Here is the constraint of optimization problem we need to solve. We denote the input images as IR and ID, and use triangulated height fields with colored triangle faces to represent the input mesh S and output mesh SD. The first inequality constraint is used to bound the movement of each vertex to be less than a given threshold delta. The second one The second one constrains the color value within the range from 0 to 1. And H is the height vector of SD, and C is its color vector. Ci is the height of the corresponding vertex in S. We define a visual as the sum of the squared Frobenius norm of the color difference between the input and the rendered images. E deform is defined as the squared L2 distance between the Laplacian of the height fields. A W is a positive weight. Since we can easily obtain a set of initial H and C values that satisfy the hard constraints, we propose using barrier functions to reformulate the above problem as an unconstrained optimization problem. In this case, with differentiable rendering technology, we can easily obtain gradients of the objective function. Hence, gradient-based numerical optimizers such as the add-on can be applied to solve our problem. However, there are two challenges. First, rendering the reflected image IRP needs a differentiable ray tracer, which is computationally expensive and prohibitive. This makes our algorithm unbearably slow to run. Second, the visual fidelity requirement and the shape preserving requirement are conflict. It is challenging to achieve a good trade-off between these two requirements. We propose two key techniques to overcome the two challenges. First, instead of using ray tracer to render the reflected images IRP, we choose to compute the reflected shape of SD, since the mirror cup is assumed to be a cylindrical surface. Each point in 3D must have the same height as its reflection in the mirror cup. Hence, we reformulate the problem as a 2D geometry problem. Note that straight line segments becomes curved after reflection. However, with the high resolution meshes that we use, we can approximate each reflected mesh edge as a straight line segment. Therefore, we only need to compute the reflected positions for verticals. Then the reflected shape is rendered into IRP using the differentiable rasterization technique, avoiding the need for large computational resources. In our algorithm, the soft rast proposed by Shichen Liu and others is used by us. The second one is a conflict reduction strategy. During our experiments, we observed that when pixels in IR and ID corresponding to the conflict area share similar colors, the visual difference is small and the conflict area remains as a result. This shows that we need some way to enhance the differences in the colors of the conflict areas. And we also find that smooth regions in the input surface are prone to induce conflict areas, which means we need to generate some spikes on the saucer to further reduce the conflict area. To reduce as many conflict areas as possible while maintaining low geometry distortion, we propose two methods based on their cost. The black-white shape enhancement technique and the sparse spike strategy. We replace the input image images IR and ID with images containing contrasting colors. So the new visual fidelity term becomes the difference between the black-white enhancement images and the rendered images. This step tries to separate the sorter into two sets of areas. One set is directly seen by the reviewer, while the other is indirectly seen by the reviewer via a reflection in the mirror. The sparse spike strategy is to replace the distortion term with the sparse spike energy term. This step aims to further reduce the conflict areas after the black-white enhancement. As shown in the figure, spikes on the surface helps separate the conflict areas. However, these spikes imply high geometry distortion. So we allow only a few spikes, which are formed by moving as few verticals as possible. And next, we introduce our algorithm pipeline. First, we use a black-white enhancement images to replace the input images. And then we optimize this problem to get a preliminary result. Second, the sparse spike strategy is used to allow few spikes in the source surface so that the conflict area is further reduced. The problem is optimized by combining the Adamax algorithm with the proximal gradient method. After that, we project the input images onto the sorter to generate texture. The remaining conflict areas colors are set to the average of the colors of the corresponding pixels in the input images. In our experiment, we find that it is difficult to find universal balance weights for different inputs, as they have drastically different visual fidelity energies and shape preserving energies. Therefore, we propose an input relevant scheme to automatically set balance weights. We measure the compatibility between the input images and input surface as follows. First, texture the input mesh S temporarily with IDE by reversing the perspective projection process. Then the reflection of the mesh in the mirror is rendered to produce a reflected image, denoted as IRC. Second, generate another temporary texture surface by projecting IRE onto the reflected shape of S, and render the temporary texture shape to obtain a directly reviewed image, denoted as IDC. And last, compute the compatibility score. This score reflects whether the input mesh shape fits the input images. So we use it as a reference value for the weight setting. After extensive testing, we set the weights to be a constant multiples of the compatibility score and fix them throughout our experiments. Here we show the comparison result of our key techniques. From left to right is the result without any key techniques. The result only use black-white enhancement, and our result. We can see our result has the lowest visual difference. We also perform a stress test of our method with 3 typical input surfaces, along with 3 different input images. The figure demonstrated the robustness of our algorithm. The second column shows giving either a plane or a random height field as the input shape, our algorithm manages to produce a high-quality result instead of getting stuck in a suboptimal local solution. The third row shows that when the input shape is sufficient, our algorithm can optimize only the texture of the saucer while the shape remains fixed. As seen in these examples, our framework does not enforce any constraints on the input shape, and instead it takes any shape. Although the resulting shape can be very different from the input in certain cases, such as plan. When the mirror cup is a regular angular prism, our method allows multiple reflected images as input. As shown in the figure, the area on the saucer that is reflected onto the cup does not cover the entire surface. With two placement options for the cup, we are able to generate two reflected images, and each of them corresponds to one reflection area. When generating two reflected images, some details are different from our default cylinder case. First, two reflected shapes must be computed. Second, the visual fidelity energy contains 3 terms, 2 for the reflection and 1 for the direct view. Third, the black-white enhanced images become solid color enhanced images. We fill in the colored region of the 3 input images with red, green, and blue respectively, and the other regions are filled in with white. Here are some examples of the multiple reflection images. We collect 23 different images and 5 surface shapes as input for our method. Here are the results with 18 combinations. For the 5 remaining examples, we use 3D printing technology to manufacture them. Next is a video showing the result of the 3D printing. This result shows that our method is indeed robust for different input images and saucer shapes in practice. So to conclude, we propose a computational tool for automatically design mirror cup and source artwork. It can help users produce mirror cup and source art with desired images and source surfaces. And our algorithm is robust enough with different inputs and has no additional requirement on input source shape. To balance the trade-off between visual fidelity and shape preservation, our system allows users to adjust the weight in the objective functions. For example, large weights can reduce surface deformation while allowing greater image difference. We have demonstrated the capability and the practicality of our method on an extensive set with 46 examples. However, there are also some limitations. First, in practice, real users' perspectives may not exactly match a specified resume position and direction, which causes apparent resume distortion. We believe that this can be avoided by adding visual distortion for some offset resume positions into the visual fidelity energy term. The second one is that the printed color is blurred due to the penetration of differently colored printing material at the surface edges. Recently, some researchers have developed solutions to this very problem. In the future, we would like to integrate these solutions into our system. Third, in this work, we choose not to color the areas of the source surface that are invisible in the input resume direction. In general, reviewers tend to prefer a source surface with an overall continuous and smooth texture, which makes it look more pleasant when viewed from other directions. In the future work, it is worth considering the smoothness of color transition over the source surface. Last, due to the long running time of our method, it is currently infeasible to provide an interactive user interface for design. Consequently, it is challenging to incorporate users' design intention into the resulting mirror cup art. In the future, we wish to speed up our system using more efficient differentiable rendering technologies and numerical solvers, thereby enabling an interactive user interface. Thank you.
Okay, thank you, Kang, for the very nice talk. So, I mean, it's very exciting to see this very nice mirror cup and source art, designed by your computational tool. So I have a quick question for Wu Kang. So in your work, right? So I think you assume the cup it has a cylindrical shape. Right? I mean, so that if, at least from your results, the cup is always a cylinder. So my question is there any challenge to generalize your algorithm to a cup that have a shape that is not a cylinder? We know, not every cup has a cylindrical shape.
This is because we need to calculate the reflection shape of the mesh, and when the cup is a cylindrical surface, it can be formulated as a 2D geometry problem. And if the shape is not a cylindrical surface, it is quite hard to calculate the shape.
So in that case, well, I know, one key idea is to use this reflected shape construction to speed up the rendering, right? So yes. If that method can be generalized, for long cylindrical shape, or if you cannot, then will you need to use this differential rendering to address this problem?
If the shape is not a cylindrical surface, we need to use the differentiable ray tracer to do this.
Okay. Yeah. Okay. Okay. That clarifies my question. Okay. Thank you. Okay. I have one technical question for Xiaoming. So in your work, actually, you introduced 4 interesting works on computational art, and I'm quite interested about this work about fabricating a 3D shape with a few template triangles. Okay, so in your work, in that work, I think you take a single mesh as input, right? So my question is, can I take multiple meshes as input? To use a minimum number of template triangles to approximate them. Will the algorithm be the same?
Yes, I know the question, and I know yes. The goal of that work of the usability, we in practice, we just use 9 template triangles for all fabricated shapes. So although the algorithm is take one shape as input, actually the template shapes, template triangles can be used to other shapes. So no matter how many the input shapes, the template can be reused for any shapes.
Okay,
Yes,
yeah, I think that makes sense, right? I mean, because if there are multiple shapes, I mean, you can consider as a mesh with disconnected components, right? I mean, actually, I mean, in terms of geometry, there's not much difference. Okay, yeah, I have one more question is, in your work, actually, you have 9 template triangles. Have you studied the number of template triangles on the I mean the performance of your algorithm? For example, the approximation accuracy, these kind of things. For example, if I increase the number of templates.
Well, in common sense, with the more template triangles, the approximation will decrease. But there is no strict guarantee that this will happen. But more in practice, the more templates, the smaller approximation errors. In our paper, we have tested different template triangles, but in real fabrication, we just use 9 template triangles.
Okay. Yeah. Yeah. I mean, a few templates actually can make the fabrication easier.
Yeah.
Okay,
if you we also test some extreme cases. For example, 1 template or 2 templates. Okay. Then the algorithm may fail. Yeah. Yeah. Since maybe the approximation will be the approximation error will be very large, and some constraints will be violated. Yes.
Yes, I can imagine that. Okay, so I think I would like to discuss a few high-level questions. Maybe for both of you. One question is, I mean, we know for traditionally only artists can do the artwork, right? And now, I mean, we study computational art. So basically, we want to develop computational tools to design artwork. I mean, even either for the professionals or for the general users. My question is, so what is the benefit of the computational art? And also, what is the challenges, I mean, of computational art compared with traditional methods to create artwork?
In our research actually, we find many art that may be realized using a computational tool. But the key challenge I found that is how to formulate the art design process into mathematical models that can be solved by the existing tools. For example, for the visual art, yes, we can use differentiable rendering techniques to assist us for the design. But in many artworks, there are no suitable tools that can be used for modeling the artwork, thereby enabling us to perform the optimization, modeling, and so on.
Okay, and yeah, and I understand that. I mean, the modeling, the mathematical foundation is a challenge. And do you think the evaluation will be a problem? That means even you can use a computer to design a piece of artwork, but it will be difficult to evaluate automatically. I mean, actually, this is quite common. I mean, even for some 2D visual art, right? So do you think this evaluation will be will be also a challenge.
Yes. In our works, actually we fabricate many works, but the fabrication process is still very time consuming and tedious, and so I think one possible one challenge maybe from the we need some engineer to assist us to do some fabrication. This is also very challenging. If we have such, if no students can perform this, then the evaluation part will become challenging. Yes, in our in my introduced work, the evaluation part, for example, for the chebyshev nets, to make one discrete Chebyshev net, we usually need 2 days maybe. This is very time-consuming and hard work. So I agree with you that the evaluation part is often very challenging.
Yeah. Okay. I knew. I mean, the fabrication is one. I mean, is necessary for the evaluation, right? So I just wondering, even after you fabricate the shape, right? So do you need to find some professional artist to say this is a piece of good artwork? I mean,
Oh.
I mean,
in our work, we recently we focused on the works that the artworks that have been realized by the artist. Okay. So for our work, in our work, we just compare our result with the artist artworks. Okay. So if they are similar, we think our artworks may be acceptable or good. If for some creatively artworks or that are not realized by previous artists, I think the evaluation may be use some questionnaire or other tools. Are you study to? Yes, maybe you study.
Yeah, I think.
Yeah, yes.
Yeah, I think. Yeah, I think that would be the. I mean, the traditional way to. I mean, the good way to do that. Do the evaluation. Mm. Okay, thanks, Xiaoming. Okay, I have one question for Kang. So I think at the beginning of your talk, actually give very nice overview of this existing works on 3D visual art. Right? I mean, actually, I saw many of them, but only in your presentation I see you organize them very well and describe their relations. So my question is, since there are so many works on 3D visual art, so can you share your insight about what are the possible promising directions for computational design of 3D visual art?
Maybe we can, now we have the differentiable rendering technique. So I think we can do some more complex visual art. We can fusion the type of art together, such as in one visual art, we can use shadows, reflection, or we can think to create one visual art, because we have the general solution framework, we have the differentiable rendering technique. And we don't need to work as the artist to have a error and trial process to finish our work.
Okay, I think that's a good point. So I mean, we have a general computational framework, and even by this, we can, I mean, have multiple visual effects in one piece of artwork.
Yeah, yes.
Yeah. Okay, I think due to the limited time, I think that comes to the end of this talk. Thanks again for the two speakers. Give the very nice talk. Okay, thank you for joining this this seminar. Okay, bye-bye.
Okay, bye bye.